I have you loud and clear.
Hello.
Welcome. Science.
And that is to say,
physics,
Medicine.
nature,
or
Space. Time.
The brain. Life.
The universe.
Hello, this week we have a special show for you recorded at the Cambridge Science Festival. We're at the Cambridge Science Centre alongside this extremely lively audience. I am Chris Smith from the Naked Scientist team, and also here is BBC presenter and erstwhile science buff, Chris Barrow. Hi, Chris.
Hi there, and in store for you this week, 6 of Cambridge's finest researchers. They're here to strut their stuff and give us a peek into the surprising world of science that they're working on.
Right, now, Chris, are you of the competitive persuasion?
Well, you know me, Chris. I'm always happy to put my money where my mouth is.
Well, it's very lucky for you that you're a gambling man, because we have decided to split our scientists into 2 teams. There's going to be Team Barrow and Team Smith. Now, they're going to be indulging in a scientific grown-up version of show and tell. And we'll also be testing whether they can tell some science facts from some science fiction that we made up. And then at the end of the show, we're going to be asking our audience to vote on which team has the coolest, most incredible, and the most life-changing science to display. So who do you think is going to win?
Well, I don't think there's any doubt. I think I've got the advantage because you mentioned cool, incredible, life-changing. I mean, if we're going on charisma alone, then I think our team is out in front.
Don't forget modesty too, Chris. That's very important. Well, let's meet Chris's crew. On Team Barrow, is she an engineer or is she a biologist? In fact, she is both. Dr. Krishna Mahbubani from the Department of Chemical Engineering and Biotechnology. She's got a PhD in being a vampire. That's because she makes freeze-dried blood. Next up, hoping his circuits aren't going to break, that's Dr. Stuart Higgins. He's from the Cavendish Laboratory, where he's making flexible electronics, so your milk bottle can tell when your milk bottle's about to turn into cheese. And also, finally, can he lift his team to the top? The engineering department's master of gravity, Hugh Hunt. Let's give them all a round of applause.
Well, what a team, can I just say firstly, and it sounds like a bunch of winners to me. So, Chris, let's see who's in your corner. She's got the secrets of teamwork, but will it help her today? Psychologist Gabriella Pavarini, who looks at how people get their actions in sync, trying to turbocharge cereal crops so they grow better. So maybe he can get a big portion of oats in the morning. Is plant scientist Howard Griffiths. And last, but by no means least, the lady seeking to revolutionise how we make things move and transmit electricity. That's Sechutra superconductor Sebastian. Give them all a round of applause.
Let's move on to the first Team Barrow contestant. That's Krishna Mahbubani. So, Krishna, what have you brought along today?
So today I've brought for you some freeze-dried blood, some actual blood, and also some tomatoes and dried pineapples.
What are you going to make, a pizza?
Well, not exactly. I'm going to show you how and why I freeze-dry blood. So I've got some tomatoes here who are just similar to your red blood cells. They're round, they have a membrane on the outside of them, and they're full of liquid inside.
They're also in a plastic bag.
Well, that's more just so, they're easy to carry around, just like your blood vessels. So I have some tomatoes here, which I then froze. As you can see here, they're kind of solid. You can have a little feel.
They are pretty hard, yeah.
Now, I then allow them to thaw out. And what I had now, having frozen and thawed out my tomatoes, they kind of look quite grim and gross. And
If I give these a squeeze, they're quite squidgy.
Yeah, they're pretty much not going to be there very much. So this is the problem with trying to freeze things. If you don't freeze them properly and carefully, when you thaw them out, they just turn to mush.
Why does that happen?
Well, that's because when water freezes, it actually expands. So all the water inside your cells expands and cause the membrane on the outside to explode.
You make big ice crystals inside the cells, which busts them open.
Absolutely. So that's pretty much what happens when you freeze them, and when you thaw them, the same thing happens. As you thaw them, the water expands up when it comes up to about 4 degrees, and that causes any residual cells that hadn't quite exploded before to explode again.
So I can see the problem with blood. If we just took a blood sample from a person and put that in the freezer, all the blood cells would basically bust open.
Yeah.
The blood would become useless.
Absolutely. All you'll have is the red material inside your blood, which is the hemoglobin, which really does work by absorbing the oxygen onto it, but without the cell around it, it won't go anywhere in your body. So it's kind of useless.
Why do we need to freeze blood at all? Or why would that be useful?
Well, blood at the moment, when we take it, we put it in the fridge, and it can only be stored for a very short period of time. And that means that we can't really store it. We can't actually move it to places where we need it as well. So when people are at war and we want to transport blood out to them, we can't really do that because it's very tricky to keep the temperature constant so that the blood stays where you want it to be and in the best condition.
And also, it's better to have your own blood, isn't it, if you can?
Absolutely. If you had the opportunity of wandering around with a bag of your own dried blood in your backpack, if anything were to happen to you, you just mix the pack together so the liquid mixes with your dry blood, and then off you go. They can actually medically put the blood back into you, and you're good to go.
Have you got it working?
Well, not quite there yet. Chris loves to ask me this question, but I'm not a big fan of answering it. I'm still working on it, and it's getting better.
Okay, so what are you doing to try to make it so blood can be frozen? And what is this in front of us? Is this examples of it?
Yeah, so here's some examples of it. So I've got some blood that I try to freeze dry. Rather than just freeze alone, which is quite tricky, what I do is I freeze the blood in small little vials, because obviously I don't want to use loads of it initially when I'm doing different tests. So I freeze small amounts of it, and then what I do is I pull the pressure down. So I make it very cold and make it very low pressure. And what that does is it changes the boiling point of water within the blood. And so at that pressure, I'm able to boil the water out, even though the temperature is well below zero. So as a result, I can end up with a very dry cake. And they use this technique for fruits and vegetables. So I have here some freeze-dried pineapple, which Chris can have a little taster of. It's quite crunchy.
Okay, so these are literally just chunks of yellow stuff, and
Yeah.
they don't look that appetising, but
They're
I'll eat
not
it.
very They don't look very tasty, but they're absolutely fine.
Okay, yeah, it's pineapple.
It does taste like pineapple, and the idea that I'm using for my freeze-dried blood is that you can just add water. So what we did earlier was add some pineapple into a jar, and then we added a bit of water into it. And now we've just let it rehydrate again, and what you have are swollen up, looking like quite regular pineapple.
It does look like, it doesn't look great, but it does look like pineapple.
It does actually look
tastes all right.
Yeah, it actually tastes like pineapple.
But you wouldn't want to inject that into somebody, though, would you? That wouldn't make a good
Probably not.
blood transfusion.
No, it
So how do you turn the pineapple trick into blood that will work?
So what we have are little cakes of blood, and the idea is that we'll have two packs next to each other, so you can actually just mush the liquid straight into the blood.
That's a scientific term, mush.
Well, not really, but the idea is it's going to be in soft packs, so you can actually squeeze the two packs together to allow the whole mixture to come together. And what we do is we add it together.
Because we've got a little bottle here, and it looks like a big pill, actually, of sort of browny red stuff
Yeah.
in the bottom, and you've just added about half a bottle in this little bottle of water.
Yeah, so what it is just a cake of blood, because it's effectively just the blood dried up with all the water removed. And now all I've done is add a bit of water to it, and I've shaken it up, and it's gone back into its liquid form. Now here, it looks much darker than the red blood. That's because I haven't oxygenated the water to make it go red, which is what makes your blood nice and red. So it's a bit darker just because there's not much oxygen in it.
And if I put this reconstituted, freeze-dried, or previously freeze-dried blood under the microscope, do I actually see blood cells
Yeah,
in there,
you
or
would
do I just see a mess?
No, you'd actually see quite a few blood cells in there.
Quite a few,
Not
or
as
like
much.
how many? What percentage? Come on.
About 8% of blood cells in there compared to the regular what I started with. So, it's
So
not
there's a
that
little way to go,
There's
but the fact is,
yeah.
when I spoke to you a few years ago, it was much worse than that. So you actually made quite substantial progress.
8% is a significant improvement already, but I've got a fair way to go.
And how have you made that difference? What have you done to mean that you're now getting almost 1 in 10 of the cells you freeze actually coming back to life?
So what we've done is we've added different materials into it, known as cryoprotectants or lyoprotectants. So we add these things to stop the damage happening during the freezing and during the drying process. And we're starting to look at different things we can add to the blood that are not toxic and not bad for us, so that when we do transfuse them back into ourselves, we don't have to remove them. And that is helping to keep the cells stronger and alive, and it's also maintaining the chemical structure within the cells.
I've got a very important question, and that's how far are we away from being able to freeze dry a whole person?
We're actually a very, very long way away from that. And that is very simple. It's because ice, when it forms, is an excellent insulator. So when the ice forms on the outside, the inside of you doesn't freeze up fast enough. And so because you're a very large person, and you're not a tiny little cell, it's going to take a very long time to get you to freeze all the way down the middle. And it's going to take a very, very long time to get all of that water out as well. So right now, not really possible.
Krishna Mahbubani from the Department of Biotechnology. Thank you very much.
Hello, Greer Jackson here. I just wanted to interrupt and tell you what exciting things I have in store for the Naked Astronomy podcast this month. Take a listen to this. Scientists are calling this a revolution in the world of cosmology. It's a gravitational wave, of course. Join me, Greer Jackson, on Naked Astronomy to hear how this elusive phenomenon is making waves. It's available on most podcasting platforms or from nakedscientist.com/astronomy.
This is The Naked Scientists with me, Chris Smith, and also with Chris Barrow.
Now let's take a break from the competition because this show is coming to you straight from the Science Festival, but it's just one of hundreds of events. Festival coordinator Lucinda Spokes explains more.
Good evening, everybody, and welcome to the Cambridge Science Festival. It's day 2, and people are still standing.
We run for 14 days. We have this year 350 events, and we hope to reach at least 45,000 people. So the theme is data and knowledge. We're collecting and generating so much more data than we've ever done in the past. So an interesting thing about whether all the data we collect makes us perhaps cleverer. It allows us to show some of the amazing science that we do here in Cambridge. It allows us to work with partners from both within the university but also external to the university, and we hope that the University of Cambridge and all of our partners show the amazing scientific community that is here in Cambridge and allows us to share it with thousands of people. What actually the festival gives is a space and a safe space for people to discuss scientific issues. So we firmly believe that this is not us telling people about science, it's about engaging in a two-way conversation. So the things that are concerning people, the things that are interesting people, the subjects that concern and interest people, and giving people a space and a time to actually voice their opinions, their views, their excitement, their worries about some of the big advances in science that are happening today that potentially will change our future.
That was Cambridge Science Festival's Lucinda Spokes.
Coming up shortly, can Cambridge scientists tell science fact from science fiction? We'll put their knowledge to the test. But for now, I think Team Smith have got their work cut out to do something more life-changing than freeze-dried blood.
I was quite impressed with that, and that's very true, but don't get too comfortable, Chris, because my first team member studies teamwork for a living. That's psychologist Gabriella Pavarini. And Gabriella, I think you want to start with a bit of an audience participation activity.
Yes, that's right. So we're going to be doing some movements together, and that's going to create the sound of rain. And I'm going to go through the movements with you, and Chris is going to describe them for you, okay?
Okay, so the first movement, rubbing your palms together like you want to warm them up. Good, okay. Then we're clicking fingers and thumbs. Okay. Now you're tapping 2 fingers from one hand on 2 fingers of the other hand. Now you're just having the clap. Now you're clapping your palms against your thighs. Jumping on the spot.
That's right. And that's it.
And that's the lot. Okay, that's what we're going to do.
Yeah, so we're going to go through all those movements and then go backwards.
So reverse the order. Do them again, but in the reverse order.
Yes, that's right.
Off you go. It's over to you.
So we can start right now.
Very good. I think you can give yourselves a round of applause. Right, okay. What did that prove?
That's a demonstration of the type of research I do. So my work is focused on behavioral synchrony. Basically what I study is our ability to entrain our movements with the movements of other people. And that's called entrainment or synchrony.
Why is that important?
So we find that when people engage in those types of activities, could be either music making, drumming, dancing together, etc., they tend to like each other more and They cooperate more, they feel closer to one another, more similar to one another. So basically, it's a mechanism to facilitate cooperation and social bonding.
Many people would say that's not rocket science. If you give people instructions, you can get them to copy it.
Right, I mean, we synchronize naturally, so people tend to fall in sync with each other from very early on in life. When you listen to music, we tend to move to the sound of music. So that's a very basic human capability.
Are you saying then that sort of hardwired into all of our brains is the ability to fall into step with each other, whether we like it or not?
Yes, that's right. And those types of activities, they're seen everywhere. So regardless of what type of society it is, how big it is, how small it is, how complex it is, they always stop at some point to sing or dance together, which is quite interesting.
Well, Chris is a musician. Is this actually part of the reason why when we go and see a big orchestra play, people can all keep time with each other?
Yes, that's right. So music is very related to that. And music gives the possibility of a big group bonding together because they're all following a common beat.
It was interesting. You were almost conducting everybody like a conductor conducting an orchestra, for example. It did seem very much like that, and I definitely see the transfer. Is there other implications with sport as well? Does this transfer over to sport?
Yes, for sure. So we did some studies with rowers, for example, that we asked them to row in synchrony versus out of synchrony using an indoor machine. And then we see some convergence in terms of motion states when they row in synchrony with one another. And there is also other research showing that if you synchronize, you tend to cooperate better.
Now, that's all kind of good stuff, isn't it? We're kind of getting together, playing sport really well, playing music really well. Are there any examples of where it's a bad thing?
Yes, it's certainly not all good. For example, there was one study that I ran in the lab in which people synchronize with each other with a simple tapping task, such the one we did right now. And then half of the participants did that activity in synchrony. So they listened to the same music and they were tapping some cups together. And then the other half of the participants did the same, but out of synchrony. So they were listening to different songs. And then after that, they were asked to drink some quite nasty drinks. And basically then we asked them about the taste of the drinks, we coded their facial expression, and we looked at we asked them how reluctant they were to taste that new beverage. And basically if they had been in synchrony with the other person, they reported being less reluctant to drink. And for some participants, those who were quite sensitive, those actually expressed less disgust towards the drink when they had been in synchrony with somebody else.
So that might explain why school meals, despite being disgusting, are nonetheless eaten en masse.
Yes, that's true. So you need to get the kids all to synchronize before you send them out to the break.
And then they'll eat anything. Gabriella Pavarini, thank you very much.
Chris, I think your team has an unfair advantage. I mean, you've got an expert on your side. We mentioned music earlier. Did your team have a sing-along just before the show? Because
we thought about it. We were out in the street doing a haka, actually. And that's why we've kind of all pepped up and pumped up. And we're really going to take you by storm, Chris.
OK, we'll bring it on. That's what I say.
I wouldn't worry, though, Chris. I think you're still in with a chance, because up next is Naked Scientist regular and circuit bender extraordinaire, and that's Stuart Higgins. Stuart, what have you got there?
So, Chris, in my left hand, I have a silicon wafer. It's a kind of shiny blue colour. It looks very metallic, and it's very hard. And if I was to drop this, it would smash like glass.
It's a disc. It's, 4 or 5 centimetres across and thin, shiny. It's like a CD, really.
Yeah, it looks very similar to a CD. It's got the same kind of rainbow colours if you look at the surface of it. This is silicon, so if you think in terms of your phone and the chips inside your phone or your computer, this is what they're made on. This is this hard material. Now, that's great, but as I said, if I drop this, it's going to smash. It's not going to be so good. What if there was a way that we could make electronics using plastic with the benefits of plastic, but also the electrical benefits of silicon?
Why would you want to do that?
Has anyone ever dropped their smartphone? So if you drop something like a glass screen, or you drop something that's a hard crystal substance like silicon, it's going to smash, it's going to shatter into lots of pieces. So I'm looking in my research at ways of taking new materials that are based on plastics that can also be semiconductors, can also be electrical in their nature. So we often think of plastics as insulators. That's why we make our plug sockets out of them. That's why we make our cables out of them, because we don't want the electricity to get through. But actually, it turns out that there are special kinds of plastics that can act as conductors. They can conduct electricity, and they also act as semiconductors. And a semiconductor is something that, in the right circumstances, turns into a conductor.
And that's what you've got here, is it?
Yeah, so in my right hand, I have this flexible piece of, it's a piece of plastic.
Okay, so this is about the same size as the wafer of silicon. I can see through it. It's a completely transparent, thin piece of, looks like cling film, but a bit thicker, and it's got some coppery coloured stuff on it.
Yeah, so what we're looking at there is actually this gold. So if you look closely at the substrate, you see this kind of pattern of gold wiring, essentially. And all of these wires are connected together with little devices called transistors. And a transistor is a switch. It's like an electrical switch where you press it and turn it on, you turn it off. And it's the fundamental building block inside every microprocessor. So when your computer does calculations, it's transistors that are switching on and off.
How might we make that?
The benefits of plastics are that you can actually turn them into inks. So if you're doing something like silicon, you have to use very industrial processes, very hard material to work with. But if you've got a semiconductor that's also a plastic, you can dissolve it, you can turn it into an ink that could go into a printer, for example, an inkjet printer like we have at home. So one of the things we look at is ways of printing circuits on plastic. We send the design from the computer to the printer and it prints out the circuit on the piece of plastic. And in that way, we're looking at ways of building up layers and creating these kind of flexible circuits.
And what sorts of things could you make that do with that same technology? Because I know what my phone can do, but am I close to having a roll-up phone?
You're a little away from it yet because the silicon technology is so far developed. It's had many, many years developed. The phone inside your pocket has 1 billion transistors in it. Incredibly complicated. This piece of plastic I have here has 120 transistors. We're still years and years behind. But one of the things we are looking at doing is incorporating it into other kinds of products. So in my particular research, I look at radio tags. And I'm interested in seeing whether we could make a flexible radio tag, a bit like your smart card or a security card when you swipe it on a door. And looking at ways we can make that onto a flexible substrate. And the reason for doing that is that if you can make things flexible and you can print circuits, and you can do that cheaply and easily, then you can think about putting circuits where you wouldn't normally find them. So, for example, maybe on packaging. So as you referred to earlier, imagine having a milk carton in your fridge that was talking to the fridge itself and could actually tell you when the milk is about to go off. Or that you know, by looking at your smartphone, what's in your fridge when you're out shopping so you know what to buy next.
Be food for thought, wouldn't it?
Exactly. That's where the idea is that if we can develop new materials and we can develop processes and ways of making these circuits that do that, then it opens up a huge new range of technologies.
It's an obvious question, why are we not doing it now?
Well, the problem is that these plastics, while they're good, is they're not that good. They're still quite a lot worse than silicon. And in particular, the charges, the electricity going on inside this circuit is moving a lot slower than it would in terms of the silicon.
Now, I asked you for a bit of a demo to show us the speed of these things. What demo have you got lined up for us?
So I'm trying to illustrate here what happens if you've got a slow transistor, if you've got a slow switch that turns on and off. Now, in some ways, if you've got your smart card talking to the reader and it's kind of speaking very slowly, and you've got the reader speaking very fast in return and trying to get things very quickly, those two can't talk to each other, they can't understand each other. And in particular, if you've got transistors that can also be used as an amplifier, if that amplifier can't see all the frequencies, then you start to miss information. In this first clip, I'm going to play a spoken recording, and it's going to have all of the high frequencies cut out, as if the transistor wasn't switching fast enough. And so we're going to listen to that and try and understand what's being said and see how difficult it is to hear what's happening. And then after that, I'm going to play the second clip with all the frequencies present so we can hear what it says.
Let's do it.
I am sometimes able to eject a very fine spray of saliva out of my mouth. Why are we evolved to be able to do this?
Right, so why do they sound differently intelligible between the two?
So in that first clip, we were hearing only the low frequencies. And actually, in order to gain all the information and for our brains to be able to interpret it all, we need to have at least some of the frequencies there. We need to have a higher range of frequencies possible. So in the second clip, when we can hear everything, it's much clearer.
Well, Stuart, it's been a pleasure having you to listen to. Thank you very much for telling us all about your plastic electronics. Stuart Higgins for Team Barrow.
You're listening to a special Cambridge Science Festival edition of The Naked Scientists with me, Chris Barrow, and Chris Smith.
This week we're joined by a live audience and 6 of Cambridge University's brightest and best scientists. Now, so far we've heard from freeze-dried blood boffin Krishna Mahbubani, teamwork guru Gabriele Pavarini, and the highly flexible physicist Stuart Higgins, who's making bendy electronics.
And still waiting to blind us with science, the plant scientist seeking to pimp his porridge by making cereals grow faster. That's Professor Howard Griffiths. Pimping my porridge. Now there's a TV show, isn't there? Engineer Professor Hugh Hunt and superconducting physicist Dr. Suchitra Sebastian.
But before we hear from them, it is quiz time, because Team Barrow and Team Smith, you're going to have to please choose now a spokesperson. So who wants to speak for my bunch? So Howard's going to go for Team Smith, okay, and who wants to talk for Team Barrow?
Who we have
Who's going to be the
team?
Stuart's going to be putting himself forward. Right, what we're going to do is we will read each team 3 pieces of science trivia, and all you have to do between you may confer, is to work out whether you think this is a fact or whether it's a piece of fiction. And there will be a point for each correct answer. If you get it right, you will hear this. Okay, you get one of those. If you get it wrong, you get a... Okay. Team Barrow. Just like humans, British cows moo with regional accents. Is that science fact or science fiction?
I'm trying to think. Well, I'm from the West Country. I'm a Somerset lad, so would it be like moo? Moo?
Come on, get a move on.
Oh, no. I think true.
I think quite true.
We're going to go for true.
They're going science fact.
I'm afraid that it is fiction. This was widely reported in the UK press in 2006, so 10 years ago. They had quotes from farmers which went along these lines. Farmer Lloyd Green from Glastonbury saying, "I spent a lot of time with my wands and they definitely moo with a Somerset drawl." So it's interesting that you went down those lines. Apparently, it was all a huge misrepresentation of a professor of phonetics at University College London, who, when asked about it, said, "You could not entirely rule out the possibility, therefore the press decided that it was true." That said, some other animals do have regional accents, including whales, although they don't have Welsh accents, apparently. So there we go.
Right, next one. Ants can survive a spin in a microwave oven. Is that science fact or science fiction?
I went to California and there were these guys who were watching flies buzz around in a microwave oven and they didn't get killed.
Had they turned the microwave oven on at the time?
The microwave oven was on at the time. So I think if flies can do it, ants can probably do it too.
Yeah, ants can survive quite a lot of things. I used to attempt to eat them as a kid, and they generally survived.
What, being eaten?
Well,
What's going on in your inside?
Not quite sure. But
Did you count them on the way in and on the way out then?
No, not really.
Stuart, what's the verdict of your team?
Well, I think there's not much water in ants, so I think we're lending ourselves towards true. Ants will survive.
They're saying science fact.
Yes, it is, in fact, a fact. Microwaves are actual waves. They're wide enough that ants can literally run away from the hotspots in the microwave to cool areas and essentially dodge the microwaves.
Right, okay, next one. You ready for your third and final science fact or science fiction? Here we go. Diamonds are made from peanut butter. Science fact or science fiction?
Diamonds are made from... Well, diamonds are pure carbon.
Diamonds are forever as well.
Peanuts have a lot of carbon, a lot of energy in them.
Well, maybe if you ground down your peanuts and you got all the carbon out of them, you could maybe make a synthetic one. But
Yeah, you could put enough pressure through. You'd be able to.
Stuart, have you reached a verdict?
I'm tempted to say yes.
yeah.
I can't imagine why they're asking the question, so the answer's got to be yes.
Well, we're going to go for true.
They're going science fact.
Yes, it is unbelievably true. Scientists from the University of Bayreuth in Germany used pressures higher than those found at the centre of the Earth to turn peanut butter into diamonds. They're not pure and they sometimes explode, but they form part of experiments which could tell us a lot about the formation of the Earth. So they do have a reason, apparently.
And Team Barrow, you have scored 2 points. Right, Team Smith, you have 2 points to beat. Here we go. Darth Vader, Beyoncé, and Donald Trump all have animals named after them. Science fact or science fiction?
I think it's extremely likely because I think it is quite possible.
Okay, Howard, have you got a verdict?
We'll go true.
Well, this is a very cheeky question that's false. While Darth Vader and Beyoncé do have animals named after them, Donald Trump is yet to have this scientific accolade. Scapacia Beyonce is a horsefly with a glamorous golden abdomen, apparently. Darth Vaderum is a type of mite. But there is a caterpillar called M. opercularis, which is sometimes called the Trump caterpillar because it looks like his hair.
Next one, you ready? It takes a radio message from Earth about 1 day to get to the New Horizons probe out near the dwarf planet Pluto. Is that science fact or science fiction?
Physicists, come on, what do you think? Pluto, 1 day to get to Pluto, radio wave.
Yeah. Fact. Okay.
You think we think fact.
Okay, they're going science fact.
Oh dear. No, it is in fact fiction. Radio waves travel at the speed of light, which is about 1 billion kilometres an hour. Pluto's about 6 billion kilometres away, so messages from here take about 6 hours to get there, which is a long time, but not a day.
Right, you've got to redeem yourself on this one, or it's totally in the hands of the audience for the end, and you mustn't let me down, my team. Okay, here we go. There is a donut-shaped asteroid that scientists have named after Homer Simpson. Is that science fact or science fiction?
We're going to
Yeah,
go.
we're going to
We
go.
may as
Fact.
well go
Yeah,
fact.
yeah,
It's fine.
might as well, yeah.
We're going to go
It's our
fact
favorite
again.
answer.
Science fact. You're doing very well. You got 0. Well done. Excellent.
Yes, unbelievably, or rather, not unbelievably, it is fiction. Asteroid belts are often the shape of donuts, but no donut-shaped asteroids have ever been seen yet.
So the winners at this halfway stage, 2 points to 0. Team Barrow! Now let's get back to our scientists, and I'm hoping that Professor Howard Griffiths is going to serve up a win for the team. We really need one, Howard. And now, Howard, why are you wandering around with what looks like the contents of a cornfield?
Well, it is the contents of a cornfield, and what I'd like to do is hand out some of these to some of these youngsters here.
What are you dishing out?
Well, I'm giving out some ears of wheat that I collected from a field, and it illustrates. How many of you like toast for breakfast? Yeah. Excellent. Well, wheat is a staple product of the world. It feeds and it gives us a huge amount of protein. And the ears that I'm holding up in front of you contain little grains. And those little grains, if you can pull them apart and have a look, those are the seeds of the wheat. And having sown one of those seeds in the autumn, the farmer was then able to grow all these ears of wheat. And, well, these are the ones that are left behind that he didn't quite manage to harvest.
What proportion of the world relies on this simple stuff, this cereal crop, for their food?
A huge proportion of the world relies on this as a staple diet. It's one of the major protein inputs because it's got so much nitrogen in it. And so, but there is a problem with it because over the last 10 or 15 years or so, the yields from wheat have begun to plateau. They've reached a stable level. They're not increasing as much as they used to do over the previous 30 years since the Green Revolution.
Now, why is that a problem?
Well, that's a bit of a problem because the world's population is increasing, and also we're likely to get a changing climate in the future, which will mean increasingly crops won't be as productive as they have been in the past.
You're saying then we could be facing a hungry future?
Yes, indeed. And there are other issues that we need to tackle, not just about increasing the productivity of the wheat. We've got to minimise waste. I mean, for instance, these ears I picked up from the farmer hadn't managed to harvest them. And all around the world, there's a huge amount of food waste that we need to try and minimise.
So you stole that?
I helped myself, yes. It seemed liberated, I think is the word we tend to use. And also, of course, we've got to improve our distribution of these sorts of foodstuffs so that it helps people who don't have food, but also doesn't destroy their economies by distributing it in a way that would upset the national product of a particular country.
So we have a situation where yields of this very important food crop are not going up. The human population is going up. We also anticipate that the environment's going to change because of things like climate change, so that may also dent the yield. Yeah. So what's your solution?
Well, there are other sorts of plants. Now, how many of you like cornflakes? Yeah. Oh, there's... Yeah?
I'd say Kellogg's are not doing very well in this room. There's only about 2 or 3 hands up.
There are other versions of cornflakes are available from your local supermarket, you do realise. So cornflakes are made from maize, corn cob. Do you all know what a corn cob looks like? Each of those little granules on a corn cob, that's where your cornflakes come from. Now, they come from a plant that actually have a higher rate of productivity. And they've got what we call a kind of, well, we turbocharged. So naturally, this is a plant that has managed to increase its productivity by force feeding the enzyme that fixes carbon from the atmosphere.
This energy that comes to us from wheat, we get effectively from the sun, don't we? Because this plant captures the energy in the sun through the process of photosynthesis, and it stores it chemically in a form that we can then eat.
Absolutely. Plants are magnificent. When you think they take that amazing energy we get from sunlight for free and they turn it into the products that they feed us, they clothe us. How many of you have got cotton, wearing cotton at the moment? And they also fuel us. If you came in a car, that's fuel that was laid down by plants millions and millions and millions of years ago.
How can we therefore make that plant better at being a natural solar panel then?
Well, one way would be to try to take that pathway that we get in sweet corn and maize and encourage staple crops like wheat or rice to see if we could adopt that pathway into them as well.
Right, so basically take what the maize is really good at and confer that same science on the wheat. Why doesn't the wheat do that already?
It hasn't had to, because it evolved in a kind of a wet and cool environment, and whereas crops like maize come from a tropical environment where it's hot and often water limited. And so that's the advantages of that crop, as well as having this turbocharger.
How can you put this turbocharger, as you put it, into the wheat? Is that feasible?
That is a real problem, because it means that we would have to find wheat that have a slightly different structure within their leaves, which would allow us to put that pathway in. So we have an alternative solution. And that alternative solution, you can see here, I'm holding up a vial of green cells.
I thought it was a urine specimen. Look, it's in one of those pots the doctor gives you, Howard. Is that...
Chris, if your urine has got that colour, I think you do need to see a doctor.
I did have a patient with that once, and he was on a certain drug that made his wee go green. But why does it look green then? What's in that pot?
Well, this has got a microscopic alga in it. It actually grows in soil and solutions. Many of you have got buckets in your gardens that have been gathering water all over the winter. I bet they've gone a bit green, haven't they? Yeah? So that alga is all very close relatives of it. Other sorts of things that grow in ponds and in buckets and in soil.
And they're plants, are they?
They are plants indeed. They're related to plants. And they also have a mechanism which turbocharges their photosynthesis. And they do it in every single cell. So what we're wondering is they have a much simpler mechanism for concentrating that carbon dioxide and improving the efficiency of the enzyme. Could we try to persuade all the cells in a plant like wheat, if they could adopt that mechanism, and maybe that would improve their photosynthesis, and that would help us increase that yield of wheat and rice and so on by 10 or 20%, which is what we will need to do over the next 50 to 100 years.
You're saying take the machinery from the stuff that makes the pots in your garden go green and put that into wheat, and it would be like putting a Porsche engine into a larder.
Indeed, that is the sort of idea, yes. Yeah. I hadn't quite thought of it like that. But
is it feasible?
It is feasible. We have actually managed to get parts, little microscopic components that help to pump the carbon inside the cell walls of the alga to work inside plants.
And if you do this, what sort of increase in productivity of normal wheat might we be able to see?
Well, we would hope to see perhaps a 15% increase in wheat yields, I would imagine, would be the sort of thing that would maintain that stability for the future. In the short term, of course, we're going to rely on traditional genetics, traditional breeding that will help to bring in new traits and help to maintain pathogen resistance. But in the future, perhaps we could get away with this mechanism.
For Team Smith, Howard Griffiths.
Until people can tell you that this gene might give you an IQ of this, then we might think about, well, do we want to do that?
In this month's Naked Genetics podcast, we find out if new genome engineering tools could mean we're on the road to designer babies. Plus, we unpack the latest cancer breakthrough, and our gene of the month is making a terrible racket. Listen and download now at nakedscientist.com/genetics.
You're listening to The Naked Scientist. I'm Chris Smith and he is Chris Barrow. So we've clearly got loads of brilliant communicators with us today, but how do most early career scientists get an opportunity to dip their toes into the engagement pool? Well, FameLab is an initiative that offers that opportunity, and this year's Cambridge final was held a few days ago. Here's some of the contestants and organiser Catherine Muir.
We now can predict the future of our planet's climate and our existence on Earth. And then as you look longer, you realise that each spark lives for about a second. And in that second, it moves along a little curly path and then pops out of existence.
Ladies and gentlemen, let me introduce you to one of the greatest model organisms in biology, the worm C. elegans.
It's an international competition, and it's an opportunity to try and find the science communicators of tomorrow by getting people working in research, or both within academia or within industry, to speak about their research for 3 minutes in front of a public audience. So it's all about kind of describing what you do in layman's terms and in such a short amount of time. Similar competitions are run all over the world, from kind of like Egypt to Vietnam, Thailand. So people are all competing in their own countries, and then they come to the UK to compete in the international final. It's open to anyone over the age of 21 that's working in science or engineering or maths, so that can be within academia or within industry.
Let's imagine that these balloons are going to represent future possible you.
Stem cells, when kept in the correct conditions, can live forever.
Why we hold it within the Science Festival is the kind of educational, just getting people interested in science, but it's also really valuable for our researchers and local people working in science to be able to build their skills in communication and build their confidence in talking about their own research to a public audience. If they want to carry on with their research, it's a really valuable skill.
That was Cambridge FameLab's Catherine Muir and some of this year's contestants. Still to come, lessons in levitating, and we'll find out who wins, Team Smith or Team Barrow.
I hope you've got a trick up your sleeve, Chris, because Team Smith is soon going to be feeding the world with this amazing science here.
Well, actually, we do. We're going to stop the Arctic melting, so I want to see if you can beat that. And as strange as it might seem, Dr. Hugh Hunt and a couple of 3-foot wide balloons have got something to do with it. And Hugh, can we start off by just saying, what are these balloons doing here and why are they so big?
Well, they're balloons, helium-filled balloons, and it's all about buoyancy. And you might remember Archimedes, and he got into a bath, and he famously announced Eureka. He understood buoyancy.
He was the first naked scientist, Hugh.
Yeah, one of the first naked scientists. So I have this apple here, and when I put it into the water, it floats. And that's because the density of the apple is less than the density of the water. Now, with a helium balloon, the density of the helium is less than the density of air, which is why the balloon floats. What I'd like to do is to measure how much this helium balloon lifts. So I've got some scales here. Turn the scales on. And this apple, well, who would like to come and measure the apple? Yeah, would you like to come up? One of you, yeah, here you go.
What's your name?
Emily Warren.
Emily. So Emily, now how much is that apple weighing there? That's, if I put the apple on there, that's how many grams?
135.
Right, 135 grams. And then when I put the apple into the bag here, which is being lifted up by the helium balloon, it's
132 grams.
So how much has it got lighter?
3 grams.
3 grams. So this little balloon here is lifting only 3 grams. Thank you very much. Now, here I've got a bigger balloon. And you can see that this big balloon, well, it's already got 1 apple in there. I can put a second apple in there.
When you say big, it's 3 feet wide.
Well, yeah, it is quite big. It's about 80 centimetres wide. And what's interesting is that this balloon is about 4 times bigger than the small balloon. But because the volume goes up as the cube of the size, it's 4 times bigger, but 4 cubed is 64, 64 times bigger in volume. And 64 times 3 is about 200 grams. Now 3 grams, 200 grams. 1 apple was only 120 grams. 2 apples can't quite hold 2 apples. But you can see how that works. It's interesting with volume. We can demonstrate how things go up with the cube. I'd like to have a volunteer. Who would like to volunteer? What's your name?
Johnny.
Come here, Johnny. I'd like to do a little experiment because I want to prove that volume, your weight goes up with your size cubed. Now, your height is about 150 centimetres, And my height is about 182 centimetres. And if you do 150 divided by 182 and cube that, then that should be the ratio of our weights. 150 divided by 182, and we cube that, and that tells us the ratio of our weights is about 0.55, and I'm 80 kilograms. So you should weigh about 45 kilograms. Let's see if this works. All right, Johnny, you're going to stand on there. I reckon you should be about 45 kilograms.
So on the scales now, of course.
Oh, a bit. Okay, 34. But you should try this. If you work out your weight, it goes as the cube of your height. So someone who's half your height will be 1/8 of your weight. Now, this is really important. Thank you, Johnny. You can sit down now. This is really important because one of the things I'm interested in doing is trying to refreeze the Arctic, because we know about global warming. Well, the Arctic especially is getting very warm. And one way of doing this is to spray tiny particles up into the stratosphere. That's what volcanic eruptions do when they put tiny particles in the stratosphere, and that helps to cool the planet. Well, we could do this artificially, and we might need a very big balloon to hold up a very big hose to spray these particles up.
And what particles are they that you want to
Well,
put up?
we know that volcanoes would put up sulfur dioxide, but maybe there's other particles like titanium dioxide or silicon dioxide, tiny particles about half a micron in diameter. That's under 1,000th of a millimeter, which is about the wavelength of light, which is why these particles are good at scattering light.
And so what, you want to put them up there and they will reflect light?
And they will reflect light back into space. And we only need to reflect a tiny bit of light, and that will help to cool the planet. Getting the particles up to a height of maybe 14, 16, 18 kilometres, we could do it with aircraft, but that in itself is quite damaging to the environment. So instead, if we have a big balloon, then we can use the big balloon to lift up a hose. And one of the things about the hose is that trying to do that safely, if I have a hose, well, here's a cable here.
So it looks like you're attaching the chain from a bath plug to a 3-foot wide pink balloon at the moment. That's fairly accurate, I would say?
Yeah, so I've now got this balloon on the end of a chain, and then what happens is when you start to have the balloon going high up into the sky, the wobbling of the chain may well cause the chain to break, and this chain will be a pipe to pump stuff up into the atmosphere, and we've really got to get the engineering right to make sure that all doesn't go terribly wrong.
So something like wind would have a huge effect on this, because obviously it is going straight up into the sky.
Yeah, so wind is a real problem. The high winds in the jet stream, and big storms, and actually thinking about how we might cool the North Pole is a very pressing problem for us to deal with right now.
And does it matter that we're thinking of putting particles at that level? And people talk about the ozone layer and the fact that it's going away. Does it matter that we're starting to try and tamper with things like that?
Well, it really matters, and there's huge questions about whether we should be meddling with the atmosphere, meddling with the climate in this way. But we are already pumping 35 billion tonnes of CO2 into the atmosphere. Unless we stop doing that in a hurry, and it doesn't look like we will, we may not have any choice.
So this is possibly the answer?
Well, this is very reluctantly, it may well be the answer, but hopefully in the next 5 or 10 years we'll have figured out how to reduce our CO2 emissions.
Hugh Hunt for Team Barrow, thank you very much.
So it's time for our final scientist of the evening. And Chris, you have definitely saved something special for us.
Well, I hope so, Chris. Sukutra Sebastian is a Cambridge University physicist, and she's on a mission to transform the way that we use energy globally. And she's planning to do this with the help of a material called a superconductor. So hello, Sukutra. Can you, first of all, just tell us what actually is the problem you're trying to solve and why?
I'm trying to work toward a world in which we use less energy. If we'd like to move to renewables, like solar energy, this is made in the middle of the desert where not many people live. So to get the electricity from there to the most crowded cities, this is not easy to do.
It's a big transmission problem. You've got to move the electricity from where the sun shines to where the people live, and they're not the same.
Yeah, so if we use regular electric cables like we have here, like you plug into the wall, we actually lose quite a bit of energy. So if you put electricity through, we waste quite a bit as heat. So if we were to extend this over thousands of kilometers, you'd end up wasting a lot of that precious energy.
So you're saying it might be possible, if we can make the transmission system not lose all that energy along the way, to make lots of energy, electrical energy, where it's sunny, and transport it much more efficiently to where we need it.
Absolutely. And for this, the kind of material which I'm going to be talking about is perfect. It's known as a superconductor. It's a perfect conductor. So you're familiar with metals, conductors, in which electricity is not transported perfectly because electrons, the little objects that transport electricity, they're bumping into each other and bumping into the crystal walls. So there's a lot of energy lost because of these kinds of processes. But in superconductors, the electrons all move perfectly in sync. So when you take a superconductor, you cool it down gradually at some special temperature. They suddenly, almost by magic, all become aware of each other and all click perfectly into sync with each other. So over giant distances, over hundreds of kilometers, you get perfect transmission of
So it's a bit like, rather than having a contraflow on the motorway and everyone's going here, then everyone changing lanes and bashing into each other, we've got everyone in the same lane, no HGVs, and everyone's going along at the same speed.
Absolutely, no traffic jams. Yeah.
Is this feasible?
I can actually show you today an example of a superconductor and some of the unique and particularly exciting effects of a superconductor.
Right, let's do it. What have you got?
What I have here is I have a container. This is about minus 200 degrees Celsius, so yeah, it's quite cold.
In there's a clear liquid which is bubbling away. That's what?
This is liquid nitrogen, and this is a very effective way of cooling down whatever's in this liquid to minus 200 degrees.
Sitting in there are two very thin black squares, maybe 2 inches down each side of the square, bubbling away at the bottom. What are they?
These are actually pucks made of superconducting material. So I'm cooling them down. In order for these materials to be perfect conductors, they have to be cooled down so that the electrons start behaving in sync with each other.
When we've got them really cold, what are we going to do with them?
Okay, so what you see here is a giant ring. So, well, when I say giant, it's about 1 meter across. You see these shiny little squares? These are very strong magnets.
Right, so all the way around, it looks like a glass coffee table actually, but all around the outside rim of the coffee table are little silver squares, and those are powerful magnets.
When I put the superconductor over the magnet, you'll see what happens.
This does look magical actually, because what we've got is this glass coffee table-like thing with all these magnets around the edge, and this flat sheet of material, the superconductor that we've just put onto it, is literally whizzing around, following the path of the magnets in a circle, and it is floating about an inch off the surface.
It's floating. It can go in any direction.
You give it a nudge with the forceps, and then off it goes.
Yeah, I give it a nudge in one direction, and it goes round and round in that direction. And the only thing that would slow it down is friction, or...
From the air.
Yeah, sorry, friction from the air. Or if it were to get warmer, as it will gradually get warmer, you'll see it descending slowly.
Right, now the hard question.
Yeah.
Why is it doing that?
So to put it as simply as I can, it's because currents are set up on the surface of the superconductor.
Electrical currents.
Yes. So when perpetual currents are set up on the surface of a superconductor, it creates a magnetic field that repels the magnetic field from these very strong magnets. And so since this magnetic field of the superconductor is repelling or expelling the magnetic field from these very strong magnets, it's floating on top of this.
I get it. So the magnetic field makes an electrical current flow in the superconductor, which makes its own magnetic field,
right.
which repels the magnetic field from the table, and the two oppose each other, and it just bobs there forever.
Yeah, exactly.
Until it warms up, obviously. And the practical application of this, if we wanted to use this practically to solve the problem that you were saying at the outset, which is getting electricity around the world and that kind of thing, how could we do this?
The levitating effect that I showed you, well, for example, it's used in magnetically levitating trains to reduce friction with the track. But actually, sort of these transmission solutions are really important for the world's energy problems. And they're already used in some parts of the world. So a kilometer-long superconducting transmission line is used in Germany, for example. And actually, you've actually had your head inside one of those MRI machines, that's a superconducting magnet. So it's actually not so alien that you only see it in the laboratory. But what we really need to do to help solve these big energy problems, we need to cool it down. At the moment, the superconductors, which are best known, we need to cool them down. And this is okay in an ice cream tub in a demo or over a kilometer. Over hundreds of kilometers, this is quite challenging. And also, the material you see here...
It'd be a big ice cream tub, wouldn't it?
Yeah, you would need a lot of cooling. Yeah, lots of ice cream. Yeah, or superconductor cooling. And also, what you see here, the superconductors, you can come up and look at them. They're quite brittle. They're not actually shiny like a metal. They're not malleable. And so they're not great to make into wires, and they're quite expensive. So really, we'd like to find better superconductors.
So if you do want to improve them, how can you make them better?
We're not that great at building superconductors up from scratch, so designing them. But what we do is to take existing materials, for example, that are magnets, which are very close to being superconducting. We put giant pressures on them. Like the pressures near the Earth's core that Chris was talking about, you can create a diamond from peanut butter. Just like that, you can take a magnet, put a giant pressure on it, and make it into a superconductor. And so this is what we're doing to design superconductors in the laboratory, and hence work toward better superconductors, which don't need to be cooled, which are cheaper, and one can make these transmission lines out of.
They'd still be cool, though, wouldn't they?
They would
Sukutra,
be
Sebastian,
cool.
thank you very much.
Now, we've heard from all of our scientists, and it's time for the audience to vote. Now, we've given you all a piece of paper. On one side, it has a stethoscope. That's for Team Chris Smith, obviously.
Sue says, finger on the pulse and all that.
And on the other side, it has a pair of sunglasses. That's for Team Barrow. I think that's because we're supposed to be cool. I don't know
Indeed.
about
Well, I can hear those stethoscopes rustling. So remember, you are voting for the team that has the most amazing, in your view, groundbreaking and super cool science. So was that Chris Barrow's team, who's Krishna Vampire Mahbubani, Stuart Flexible Electronic Higgins, Hugh Helium Hunt, or was it my team, Gabriella Teamwork Pavarini, Howard Pimp My Cereal Bowl Griffiths, and Sukutra Superconductor Sebastian? Who was it? The vote is going to be worth 2 points, so we might be playing for the equaliser here. We will add it to the fact or fiction, and we'll decide who the ultimate winners are.
So first up, if you think it's my team of exceptional experts, if they impressed you the most, then hold up your sunglasses and give us a cheer. Okay, quietly confident. I think it's about 17. So
17
quietly
sunglasses.
confident.
I think this is going to be it's going to walk. We're going to walk this. If you happen to be wowed by my team of super scientists, hold up your stethoscopes and give us a cheer.
You're not going to believe this, Chris, but it's 18 for the stethoscopes by 1 point.
So what do we do then? Because my team scored an illustrious 0 on fact or fiction. Yours got 2 out of 3, and now we've got 2 votes from this. It's a draw.
It's a draw. It's the fairest way.
Well, that brings us to the end of the programme. Thank you very much to Krishna Mahbubani, Gabriella Pavarini, Stuart Higgins, Howard Griffiths, Hugh Hunt and Sukutra Sebastian. Connie Orbach was the producer, and do join us next week when we're going to be answering your latest head-scratching science questions. The Naked Scientist comes to you from Cambridge University. It's supported by the STFC, the EPSRC and Rolls-Royce. I'm Chris Smith, and thank you very much for listening.